Hello, I'm Mark Schneider. I'm the director of the Institute of Education Sciences, an independent science agency housed in the U.S. Department of Education. We have a robust agenda ahead of us. It starts with an opening keynote speaker, Dr. Bernard Harris. Dr. Harris is a former NASA astronaut who logged over 400 hours in space and traveled more than 7 million miles in space. He was the first African-American astronaut to walk in space. Dr. Harris usually shows some incredible photos of his time in space. They're literally out of this world. Since retiring from NASA in 1996, Dr. Harris has become an advocate for STEM education. He is the former CEO of the National Math and Science Initiative and remains on its board of advisors. He's also the president of Vesalius Ventures, Inc., which invests in medical technology. He's a founder of the Harris Institute, and its education priority is to help students reach their full potential in STEM. I can't imagine a better speaker to kick off the summit. Thank you, Dr. Harris, for joining us.
Hi, I'm Dr. Bernard Harris, and I'm really happy to be presenting to you today and to be a participant in this 2023 IES Math Summit. And if you know anything about me, you know that I'm a real believer in STEM education, and particularly math. I believe that having a high quality STEM education is important for our young people from several points. One is just helps them in general to be prepared for the jobs of the future. And it also is going to impact our society and our economy as a whole. And so what my plan today to do is to share with you a little bit about my background and my experience as it relates to how my career in STEM has led to such a wonderful life, and then to focus on how STEM is so important for the economic prosperity of our nation, with the portion of that is going to be focused on the pipeline, because we need young people to be prepared for those jobs of the future. And I always like to say those jobs of the now. So let's get started. So I'll start with this slide. When I was 13 years old in 1969, I followed the Apollo program. And when Apollo 11 happened, I watched that screen just like every other kid in this nation. And I wanted to follow in the footsteps of Buzz Aldrin and Neil Armstrong. And when they said those fabulous words, one small step for man, one giant leap for mankind, it was a tremendous leap for this young boy to look at that screen and to declare that he was going to follow in their footsteps. That's how it started. I also was somewhat of a geek, I will admit. I love science and I love science fiction. And so to put all of those interests together was very important to me. And being an astronaut provided that. When I got into high school, I had to figure out what field would I go into that would lead me to becoming an astronaut. Because you can't go to college and to be an astronaut, you have to choose a field. And that field for me was STEM, and particularly medicine. And in part because of another hero that I ran into that was part of the space program. His name was Joe Kerwin. Joe was the first physician to travel in space for 28 days on board the Skylab. And he became my inspiration. So I left high school, went to college as a pre-med student, went to Texas Tech Medical School, and then on to the Mayo Clinic to do my residency. And following that, I was involved in doing research around one of the biggest issues of that day, which was bone loss as it occurs in space. And I'll talk a little bit more about that in a few minutes. And so that led me to, in 1990, and I use those, that I say it that way, especially when I'm talking to young people, because many of young people and many adults weren't born then. I applied to the astronaut corps. And what you see on this slide here is my inspiration on the left, with Neil saluting the flag there, and my eventual travel into space on the space shuttle. And in the middle is the patch from my second mission. And you may not know that every mission has a mission patch, and this particular mission was going to the Russian space station. So you'll see the American and the Russian flag. You'll see the depiction of the shuttle. You'll see the depiction of the space station itself. But the most important thing about this slide and this patch is that it has my name on it there to the left. So let's go into space. Let me give you that experience. So what you're looking at right now is 3 engines of the main engines on the space shuttle. And we'll just watch this for a second. Now the vehicle weighs about 5 million pounds. And in order to get that into here, we have to light 5 engines, 3 engines on the shuttle itself, and 2 solid rocket motors that produce a total thrust of 7.5 million pounds. And I'm telling you that when these babies light, you're leaving the planet in a hurry. We pull about 1.5 Gs right on liftoff. And within 2 minutes, we reach an altitude of 100,000 feet and going a mere 2,500 miles an hour. And at that point, we come off of the solid rocket motors. You see that here. And those solid rocket motors fall back to the Earth and actually are recovered and reused. And then on the right side here, you'll see the shuttle and the external tank going on into orbit. And it only takes another 6.5 minutes and we're safely in orbit. And we'll go from that 2,500 miles an hour to eventually 17,500 miles an hour. And once we're safely inserted in orbit, we'll get off of the external tank. You see us pulling away here, pulling up. And the tank falls down and falls into the atmosphere and burns up on the way in. Once we get on orbit, this is the view, one of the first views that I saw when I was up in space. You see the nice curvature of the Earth. You'll see the tail of the space shuttle and the 2, we call them OMS pods in the back. That's where the engines are. And then the robotic arm there to the left. So what about the crew? I want to introduce you to them. So on the left side of this slide, there's 2 things I want to introduce the crew, but also introduce some of our technology. Down at the bottom on the left side are our orange suits, our launch and entry suits. They weigh 120 pounds. And the suits above, the ones that I am in, is an EVA suit, or extravehicular activity suit. It weighs 350 pounds. And so we use that when we're going outside because it's a full pressure suit, meaning that it can stand the rigors of the vacuum of space. Now, I'd like you to take a look at our faces on the left and slide over to the right, and you'll see our faces and our eyes. Faces are a little puffy. Our eyes are a little smaller than they are here on Earth. And that's one of the first changes that occurs to the human body when we go in orbit, and that is a fluid shift. So 1/5 of our blood volume is in our lower extremities. And that is held down by gravity as long as we're on Earth or another planet. As soon as we go into microgravity, then it shifts up toward the head and that extra fluid gets into the tissues of your face. And it's pretty amazing. If you asked us how we feel at the time, we'll tell you that we might have a headache. We may feel a little stuffy, like we have a head cold. And but all of that goes away within a day or so as we get used to being in that environment. One other thing I will show up with these 2 slides, I'd like you to go back to the left. I'd like you to look at me, and then right below me is Eileen Collins. She is the first, or was the first female pilot and the first female commander of the space shuttle. And look at her hair, nice and short. And rotate over to the right, and you'll see that she ends up getting an instant afro. And that's when you know you're really in microgravity. But I have one other slide I'd just like to show audiences, especially, is this slide of one of my other favorite astronauts. Her name is Marcia Ivins. And Marcia is well known for growing her hair as long as possible, and during some aspect of the meeting, she takes her hair out of a braid or a bun and just let it flow. And you might know that, look at her face, she's got a little devilish smile on her face because she knows that when she does that, nobody can get next to her because her hair is sticking out. So I mentioned just a couple of things. I'm a medical doctor, went to medical school. I also trained in aerospace medicine. And here I am examining one of our crew members in the space lab that's in the back of the cargo bay. And so some of the things that happen to you or happen to the body when we're on orbits, we lose 1% of bone per month, about 15-20% of our muscle mass. Our heart actually gets smaller, and that can go on and on and on. And I like to joke to say that all of these changes, figuring out which ones are good and which ones are bad, that's all part of an adaptive process here. I'd like to call all of that in my effort in a job security, because we're going to have humans in space, and that means that we're going to need doctors in space to ensure the health of that crew. So one of the things that we do on missions, of course, is that we have lots of experiments that we do to look at every aspect of human life on Earth. And these days, we have gone and advanced from the space shuttle to now the International Space Station. So you'll see a view of the International Space Station from the shuttle. This is from the cargo bay windows of the shuttle. You see it down there. That station is about a football field, maybe a football field and a half. It looks small here, but it's gigantic. Has several modules in which we continue to do the learning to not only ensure humans in space, but be able to experiment on different things like material processing, how do you grow food in space? Because folks, our future is going to include a part of our population living in low Earth orbit and beyond. As an astronaut, I get to see a lot of beautiful scenes. I just want to share a few of those with you. And this is a view of the Earth and part of the space station at night. And look at that dense sea of stars in the Milky Way galaxy there. And notice the limb of the Earth that glow. At night, the Earth continues to glow. It's a beautiful thing, beautiful sight. Here's a thunderstorm from space. And again, you can see that faint glow down below. And then a volcanic eruption from space. And it looks even menacing, even though we're 250 miles above the Earth. And then one view here, and I'll ask the question, I'll just pause and I'll give you the answer. What city is this? It is Cairo. If you look right dead in the middle of the photo, you'll actually see the pyramids. So it's one of the few man-made things that you can see from space, this and the Great Wall of China. And if you notice the city, it just looks like a little gray spots. You can tell that there are probably houses and buildings there, but not much else. And here's a dust storm from space. Earlier this summer, many cities in America were covered with dust similar to this. That dust comes from the Sahara Desert, goes completely over the Atlantic Ocean and dumps into the Americas. And it's been doing this for millions of years. And it's one of those things that just reminds me how we're in this closed ecosystem and how one thing can happen clear on the other side of the world and still have an impact on us. This is daytime and nighttime at the same time. And again, we're looking at Northern Africa. You'll see Spain and England to the left and the rest of Europe at nighttime. And then one of the most beautiful sights being on orbit is be able to fly through Aurora Borealis or Northern Lights. It's incredible. So you see the lights down on the planet below, and above there, it's just glowing, beautiful light show that we actually fly through. So I wanted to give you an idea of my background and my experience. Everybody wants to know what it's like to travel in space. So I hope that answered some of those questions. And now I want to change the focus to talk a little bit about what I mentioned in my introductory remarks. And that is to set the stage for what does the future hold for us? I've already talked about the International Space Station, but we're going back to the moon. And then that's going to be the jumping off spot for us to go to Mars. All of that is linked together by knowledge in STEM, in the STEM fields. And every aspect of this, since this is a math conference, involves math and those calculations of getting us from point A to point B and beyond. So we're going to have several vehicles, not just the space shuttle that's going to take us into low Earth orbit. We have companies like SpaceX and Blue Origin and Sierra Nevada. All of these are developing the next generation vehicles. So we'll have a lot more options to go into low Earth orbit and beyond. There are a number of companies that are investing lots of money. So this slide, in the past, it would just be NASA or the European Space Agency or the Japanese Space Agency. But now it's not only those agencies, it's all these other companies that I talked about, Boeing and Axiom, which is a brand new entrant. And there must be at least 20 other smaller companies that are going to be doing different aspects of low Earth orbit. So that will lead us, of course, to the Artemis program, which is the new Apollo program. Last year, we had a successful mission around the moon, and next year we'll be going to the moon. And then the year after that, we'll actually be stepping foot on the moon. And this time, not just to leave our footprints in the sand, but we will have habitat modules where we'll be living up in space for long periods of time. Just think about the implications of that. And one of those is what NASA calls the new space economy. And I'm not going to go through all of this, just to say that with private industry and with governments now looking at how we're going to take advantage of microgravity and that whole environment to advance our society forward, it's going to result in an economic or industrial revolution. And I sometimes equate it to the next industrial revolution or the next gold rush, because there are going to be plenty of opportunities out there. And why is that important? Because our kids have to be prepared for that future. So that's happening in space. And even if you don't want to go in space, you're going to be impacted by what we do in space. And even if you don't want to have anything to do with space and you want to stay here on Earth, technology is still going to be driving advancements, which then leads to, what my overall message here is that technology, STEM, including math, is involved in everything we do. On this slide, I just listed a few other things that we've been talking about, including artificial intelligence, which has hit the newspapers these days. But disruptive technology, cognitive learning, digital realities, quantum computing, robotics, all of those are going to be driven. And then the logos that I'm showing here is how it's impacting some of the most important companies and institutions here on Earth. So this statement, 9 out of 10 jobs have not been invented yet. If you think back 10, 15 years ago, we didn't have the iPhone or the iPad. We didn't have social media. Nobody could have even dreamed of those things, and yet we do have those. So I make that statement because of the history of the past and how it is predictive of where we're going in the future. So it is true. And what does it mean for you? Is that your communities, the students you serve, the jobs that you'll take, we need to make sure that we are prepared for that. And so I always ask this question: are our students prepared for that future that I just laid out for you? And usually, if I'm there, I do a poll, and usually about 3/4 of the audience will say no, and the other part will say yes. And of course, I find I fall on the no side because I've been involved in this STEM educational process for so many years because of its importance. So let me see if I can convince the other quarter of you. A few years ago, the National Academy of Sciences did a study called Rising Above the Gathering Storm, where they looked at this lack of STEM education and what the ultimate impact was going to be on the U.S. That math and science is so important to the U.S. ability to compete successfully at other countries. That this STEM basic education is required for technological innovations and the development of this skilled workforce. You probably heard of smart manufacturing. I've already talked about AI. All of these things come from knowledgeable people in STEM, but yet our American students underperform in both math and science. So we've got to do something. So just to highlight some of the problems, and again, I won't talk about all of this, but only about half of the, going back to what I said before, half of the future jobs don't exist. So in this study that was done by Deloitte, 40%, they said nearly half, 40%. And 46%, less than half of the schools offer computer science courses. Just think about that. And if you look at it from a diversity standpoint, 20% of STEM workers are people of color, only 20%. And about 17%, the last thing that I saw, of the teachers who are teaching in our traditional education systems are minorities. So we've got a lot of problems, a lot of touch points, a lot of gaps that can be addressed here to solve this problem. But we need to start working on it now. So for 15 years, as part of the National Math and Science Initiative, where our whole vision is to transform the face of STEM, meaning that we want to ensure that all our communities get a high quality STEM education, and we intend for that to result in increasing the number of minorities, economically disadvantaged populations in our community to be able to find good paying jobs. And those jobs, the highest paying jobs, of course, with STEM. So we have a mission of providing that education to people we call communities and students furthest from opportunity. And so that's our whole focus. And we do that through a number of programs where we're trying to transform our education system that will lead to the transformation, or the preparation, I should say, of our students for those jobs in the future. So I'm getting a little close to the end here, and I think I mentioned, if I didn't, I'm going to mention again, that when we're in orbit, we have to travel at a speed of 17,500 miles an hour. And that means we can go around the world every 90 minutes. We get to see a sunset or sunrise every 45 minutes. And so hopefully this will work. And I want to show you a sunrise from space. So there is the Earth below, and the sun peaks on the horizon. And within a few seconds, the sun comes full force. And the temperature will go from a minus 165 to over 200 degrees Fahrenheit. So our spaceships and our space suits must resist those extreme temperatures, including the vacuum of space. But that's it's amazing. Every time I see this slide, I could actually make this slide into a video, but I just like the cycle of the slides here. I guess that's because I'm old school. So I'm finishing up here with at our mission. And my second mission, I got a chance to do a spacewalk, and this is me and Michael Foale in those heavy suits that I described at the beginning of my talk. And we will, after this picture is taken, we will unhook from the ship and we'll go out and do our first spacewalk, both of us, our first spacewalk. On the left side, you'll see me standing up, getting ready to grab the satellite. Michael Foale is in the robotic arm and is going to be getting prepared to receive it from me. And then we deployed it, and then we had time just to hang out in space, literally hang out in space. And the little box in the middle, you heard me talk about the temperature outside. Well, we measured the ambient temperature for the very first time in space with that little box. And we worked with the National Office of Sciences and, in order to do that study. Just show you a couple of other views of the Earth below. And then one other slide. And unfortunately, that's not me. That's actually Bruce McCandless. He was the first American astronaut to use a jetpack, and he flew away from the shuttle, took some of the first pictures orbiting the shuttle, and we took the first pictures of the man in space, which is kind of cool. Okay, so this is Bruce McCandless. He was the first American astronaut to wear a jetpack and fly away from the vehicle. And he took some of the first views of the shuttle in space. And we took, of course, this beautiful view of this man in space, which I think puts things in perspective. So I want to start with this view. And when I talk to audiences, people want to know, has space or this experience changed me in any way? And I say, how can it not change you? It's an incredible experience, and I want to share that with you if I can in the next couple of slides. Imagine yourself being me on the end of the robotic arm there, looking out, not at the Earth, but looking away from space, away from the Earth, and looking into space. And then let me also ask you to extend your hand out and draw in front of you maybe a 4x4 piece of space or field of view. And this is what it might look like. And look at all of those lights and stars. It's amazing, and galaxies. In this slide, there are over 10,000 galaxies in this slide. Now, if I was to take this square that I just had you make and put it on a larger patch, let's say the whole field of view of your helmet, looking out your helmet, this is what it might look like. And that 10,000 galaxy would be there to the left. It's a lot of stars out there. It's a lot of places. I had the opportunity to meet with an astrophysicist once, and I asked him, how many galaxies are there in the known universe? And he said there's over 300 billion galaxies in the known universe. Imagine that, if you would. And of course, with that reality, I always get questions about, do I believe that there's life out there? Usually it's, do you believe in aliens? And I said, well, I don't believe in aliens, but I believe that there is life out there. And I'd like to answer that question the way that Carl Sagan answered it when he was asked that question. And he said that if there was not life, it's an awful waste of space. Think about that. There's got to be other life forms, given the extent of our universe and also the age of our universe. Which leads me to my last point. To our knowledge, the universe is infinite. It expands into whatever we don't know. But it's, to me, analogous to the child, our person, our own personal ability and potential and abilities. When I'm in a group, especially with young students, I like to remind them who they are, that they are infinite beings with infinite possibilities. And I will get them in an auditorium or in a stadium, and I'll say, repeat after me, I'm an infinite being with infinite possibilities. And we have a little war between each other. And the whole objective there is to raise their awareness of who they are, that they are born multi-potential with the ability to do anything in life, that they're born multi-talented. And we come into this world with certain talents, and then we can use our brain to learn even more. And then lastly, that each of them were born for a reason. You don't know what the impact that has when a child has that realization, and how powerful it can be in transforming them out of maybe some questionable environments to be able to see a reality of their future that is all encompassing, and that allows them to be able to reach their full potential. So feel free after this program to use this and explain it to young folks, because as we do that, it's not only going to help them, it's going to help their community and ultimately our nation. And with that, I want to say thank you so much. It's been a pleasure speaking with you.